Problem 35. We are given an equation for position as a function of time. So right away, a little bell, I hope, goes off inside your head. Ding! When I have position as a function of time, I can take the first derivative to get velocity and the second derivative to get acceleration. And they're asking me for an expression for the torque acting on the particle relative to the origin. So we have to think, what equations do we have for torque? So the two equations that we have, torque is equal to R cross F. And we also know that torque is the time rate of change of angular momentum. So we can actually do this problem two different ways. The first way we'll show you is with R cross F. Since I have my position vector as a function of time, I know I can relate F to acceleration by Newton's second law, and I can get acceleration with the second derivative of my R vector. So let's show you that solution. F is equal to mass times acceleration, where acceleration is the second derivative of the R vector. So the second derivative of this expression right here is 8 minus 12. 8I minus 12J. And then I multiply mass through there to come up with my force vector. You see it's a constant force. There is no T in the equation. Then I do R cross F. I'm using my matrix method for doing a cross product. There are my X and Y coefficients on my R vector. There are my X and Y coefficients on my force vector. Using my matrix method for solving a cross product, you can follow along the algebra. I get 48T in the positive Z direction, 48T Newton meters. Now what if I chose to do it the other way? Now I'm going to find L by doing R cross P, and then the derivative of L with respect to time is the torque. So my first derivative of my R vector is this right here. P is M times V, so R cross P is the same as M times R cross V. So there's my R vector. There's my velocity vector. I'm going to use my matrix method for solving the cross product. You can follow the algebra, multiply the 3 through the parentheses, and I get 24T squared for the angular momentum. And then torque is the time derivative of angular momentum. So the derivative of 24T squared is 48T Newton meters in the positive Z direction. The same answer that I got doing it the other way. Part B asked, is the magnitude of the particle's angular momentum relative to the origin increasing, decreasing, or unchanging? When I look at my expression for momentum, angular momentum, I see that it is positive. So as T increases, so does L. So it is increasing.